Okay, so I'm going to apologize in advance for the length of this video. This is a long topic. This is on LaGrange multipliers. Okay, so this is a way to handle optimizations over a closed constraint. The way I'm going to handle this is I'm actually going to use an example problem, and I'm going to solve the problem without using Lagrange, and then we're going to show you how Lagrange would solve this problem, and then we will use Lagrange to solve other problems. Okay, so we're going to start off with fabricating a box, and this box is going to be height z with y and length x, and it's going to be an open box, so you can look down inside of it. So the box is open. So our problem here is we want to maximize the volume of the box, which is going to be x times y times z. But we're going to be subject to a constraint. And our constraint is that the area or the amount of cardboard that's going to be used is going to be restricted to 12 cubic or square units. So we get two fronts and backs of the box. So, well, two sides. Let's do that first. 2 times xz plus 2 fronts and backs, so that's 2 times yz plus the bottom, which is xz, and we want that to be precisely equal to 12. Excuse me. So we're going to use this information to actually try to maximize the volume of the box. Okay, so given 12 units, how big of a box can I build? All right, so let's start doing some math. Okay, so we're going to start with our constraint. Our constraint tells us that 2xz plus 2yz plus xy has to be 12. Well, this means that I can move that xy over there, so 2xz plus 2yz has to equal 12 minus xy. If I factor out the z, I get z times 2x plus 2y is going to equal 12 minus xy. That's parentheses. Okay, so do a little division. Z is 12 minus xy over 2x plus 2y. And I'm reasonably assured that this box is not going to end up with both x or y having a 0 dimension. So I'm pretty cautious about that. So if I sub that into the volume, I now have xy times 12 minus xy over 2x plus 2y, which I could rewrite as 12xy minus x squared y squared all over 2x plus 2y. Okay, so what I want to do is I want to take and figure out where do I get the gradient to be 0, right? So we're going to do some work here to try to figure this out. So in order to do that, I have to take the derivative of v with respect to x. So let's do that. Okay, so this is a little bit of a challenge, just because it's tedious more than anything else. In the last screen, I got that v is 12xy minus x squared y squared over 2 times the quantity x plus y, right? I think it is 2x plus 2y, but that's fine. So if I take the derivative with respect to x, Well, let's see. I'm going to use the quotient rule here, so that's low, right, times d high, which is going to give me 12y minus 2xy, x squared y, right? Or sorry, xy squared, that should be. And then minus high, so that's 12xy minus x squared y squared, d low, which just works out to be 2, right? All over low squared, which is 4 times the quantity x plus y squared, right? So let's see what we can do. Simplifying here, this is going to become 2x plus 2y times 12y minus 2xy squared minus, and let's see, this is going to give me 24xy, and then plus 2x squared y squared all over 4 times the quantity x plus y squared. Okay, so kind of binomial multiplication here gives me 24xy minus 4x squared y cubed, or sorry, y squared, x squared y squared, plus 24y squared minus 4xy cubed minus 24xy plus 2x squared y squared all over 4 times x plus y squared. Okay, so this cancels with that, right? So let's see, I have now 24y squared, right? Let's see, minus 4 of these, so that's minus 4xy cubed. And then, let's see, I think I end up with 2 minus 2x squared y squared all over 4x plus y squared, right? Okay, so let's bring that to the next page. Okay, so we left off with this 24y squared minus 4xy cubed minus 2x squared y squared over 4x plus 4 squared. So I should be able to pull a 2y squared out, which gives me 12 minus 2xy minus x squared all over 4 times x plus 4 squared. Okay, so that's, well, let's see, we can do a little bit of a division there. Y squared is 12 minus 2xy minus x squared all over x 2x plus y squared, right? So this is Vx. You can get Vy because there's symmetry here without doing a whole lot of work. It's just going to be switch the x's and the y's. X squared 12 minus 2xy minus y squared over 2 times x plus y squared. Now, a little bit of analysis here. I need both of these to equal 0. That means I got to only look at the numerator of both. And see, y squared is not going to be 0, and x squared is not going to be 0. So I need these two guys to equal 0. So my next move is actually going to be to set those two things equal to each other. And if you look at this carefully, right, well, let's actually just do it. All right, so we're going to set those two things equal to each other. 12 minus 2xy minus x squared is equal to 12 minus 2xy minus y squared. Well, that cancels with that, that cancels with that. The negatives go away. I get x squared is equal to y squared. But we know that both x and y have to be positive because they're dimensions of a box. This is going to imply that x has to be equal to y. Okay, so that's pretty straightforward. So substitute this back in, right? So we can actually put the x into that y squared. 12 minus 2x times x minus x squared has to equal 0, right? So 12 minus, 3x squared is 0, right? Which means 3x squared is equal to 12, which means x squared is equal to 4. X has to be positive, so x is 2, which also implies that y is 2. Okay, so we also know that z, in this case, then should be 12 minus 2 times 2 over 2 times 2 plus 2 times 2, because that's our definition of z from above. So that's 12 minus 4 is 8, and 4 plus 4 is 8, which means z is 1. We have a critical point, right? The critical point is now 2, 2, 1. Okay, so let's see what that actually means. Okay, so if you want to, you can work this all out, but we know that this is actually going to be the maximum. But if you were to take the second derivative with respect to x of 2, 2, right, those are the x and y values, you're going to get negative 1. The second derivative with respect to y at 2, 2, it's also going to give me negative 1. The second cross derivative at 2, 2 gives me negative 1/2. So d is going to be negative 1 times negative 1 minus negative 1/2 squared, which is 1 plus a fourth, right? Should be, or no, 1 minus a fourth because of the square. 1 minus a fourth is 3/4, which is greater than 0. So we know that Vxx is negative 1, which is less than 0. So this implies that this is a local max. Given that it's the only critical point and this thing has to have a maximum volume, it's not just a local max, it's the absolute value, absolute max, which means the volume maximizes at 2, 2, 1, which is 2 times 2 times 1. The max volume of this box is 4 cubic units, right? So 4 cubic units. All right, so that gives us an answer. Why do we want that answer? Because later on, when we do this in a different way, we are going to see if we can solve this problem again using this LaGrange type method. So LaGrange thinks about this problem in a completely different way. He creates two functions. He creates a function of x, y, z, which is equal to the volume. He creates an x, y, z function, which is my constraint, which is my area. So that's going to be 2xz plus 2yz plus xy, and you can say that that thing is going to be stuck at 12. So he's going to say maximize this subject to this constraint. Okay, so here's the rationale that LaGrange uses, is that he doesn't know exactly what this function looks like in 3D. I'm going to kind of work this in a 2D sense. Okay, so let's say that this function g kind of looks, let's make sure it's differentiable, kind of looks like this in 2D. Okay, I have no idea, but we're going to make a g of xy. Okay, and this is going to be fixed to some number k. So there it is, g is fixed to some value. And what happens is that we look at f of xy and we say, well, what does that curve look like when it's fixed to different numbers? Okay, and those curves are all going to be parallel. Okay, so like this is when f of x, y, z, or xy, because I'm in 2 dimensions, is going to be equal to, let's say, 10. This will be what the curve looks like when it's equal to 9. This is what the curve is going to look like when it's equal to 8. 7, so forth and so on. Okay, so what LaGrange notices is that there's a point here where this level curve is actually going to be tangent to the constraint. And okay, so this is caused by what is known as convexity. Okay, so at some point we're going to have a discussion in linear algebra about why do we need convexity to have an optimization problem, but the fact that the constraint is convex is going to cause that sense of being tangent. Okay, so what LaGrange notices is that if I can find the level curve that is tangent to the constraint, okay, so like if I were to draw a line through here, this is what I mean, is that that line is tangent to both of these curves. If I can find that place, then I have the point of optimization. I either have a max or a min at that point. All right, so let's kind of back this up a little bit. Let's let f be some function that is parameterized for t. Okay, so the x, y, and z are all going to be dependent upon t, and we're going to let that be equal to some sort of constant, right? So I have my my function that I'm trying to maximize or min is going to be set equal to some constant, and it's going to happen at some value t. So if you go through like the chain rule that we worked with before, then the partial f with respect to x times dx dt plus the partial f with respect to y times dy dt, right? Plus the partial of f with respect to z at dz dt, right? dz dt, right, should give me df dt, right? I want the derivative of f to be equal to, so if I take the derivative of the left with respect to t and the derivative of the right with respect to t, I should get 0. Okay, so if you look at this, these are the three partials, right, of f. So that's going to be the gradient of f at x, y, and z, right? And these are, well, that's just r prime of t, right? dx dt, dy dt, dz dt. So if I take the gradient, and that's going to be equal to 0. So what does this mean? This means that the gradient of f, right, at that k value has to be perpendicular to r prime of t, which means that the gradient vector is perpendicular to each of the level curves. Okay, so this is kind of an interesting turnabout here, right? The gradient vector is going to be perpendicular to each of, so like if I look at the above picture here, I have that f of xy is equal to 9, and g of xy is equal to some value k, right? They have to have the same tangent line. So if these both have the same tangent line, we're going to call that tangent line r prime of t, right? It has to be, so the gradient is normal to that tangent line. Okay, so that's kind of interesting here, right? This means that these two vectors, right, the gradient of f is normal to the tangent line, right? And the gradient of g, which is also normal to the tangent line, either have to be parallel or they have to be pointing in opposite directions. And in fact, because they're coming at this from different directions, they are actually pointing in opposite directions, which means that there is some lambda, that makes these two things, these sides equal. because if f and g are pointing in opposite directions, there has to be some scalar that makes this all work out. And in fact, that lambda ends up usually being a negative number of some sort. Sorry, doesn't necessarily have to be a negative. That lambda is going to point these two vectors in opposite directions. Okay, so, well, because they're in opposite directions, there have to be a scalar within each other. Okay, so let's let that be for a minute, but this gives you the Lagrange's thinking. So I have the optimization when this occurs. So I need the x, y, z, and lambda that makes this true and the constraint. So if I have that true and the constraint being true, then I should have an optimization point. All right, so let's kind of figure out how this applies to our example. So if I look at our example, we're going to let f of x, y, z be equal to x times y times z. That's what we're going to try to optimize. G of x, y, z is equal to this 2x z plus 2yz plus xy, which is equal to 12. Right? So in order to play the Lagrange game here, I need del f, right? And which is going to be fx, fy, fz, and I need the gradient of g, which is going to be gx, gy, gz. Okay. So, and I want the lambda, x, y, and z that make del f equal to lambda times del g, and I want also g of x, y, z, x, y, z to be equal to 12. I need both of these to be true. Okay, so another way of saying this is that I need fx to equal lambda gx, fy to equal lambda gy, and fz to equal lambda gz. So this is like a system of 4 equations with 4 variables, which should have a solution. So let's see if we can find it. Right? So let's start with kind of unpacking these a bit. Okay, so fx is just going to be yz, and gx is going to be 2z plus y. Fy is going to be xz. Gy is just going to be 2z plus x. And fz is xy. Gz is 2x plus 2y. All right, so and the other thing that we need is that 2xz plus 2yz plus xy has to equal 12. All right, so if I take kind of the missing parts to each of these, I'm going to get 3 equations. So I get x, y, z is equal to, let's see, this one is mixing the x, so that's going to be lambda times 2xz plus xy. Do the second one, I get xyz is equal to lambda, and I'm missing the y, so this is going to be 2yz plus xy. And the last one is missing the z, so xyz is lambda times 2xz plus 2yz. Okay, so let's take this 2 at a time. Since they're both equal to x, y, z, I now know that lambda times 2xz plus xy should equal lambda times 2yz plus xy. So the lambdas fall off, the xy's fall off, so I know that 2xz is equal to 2yz which means x has to be equal to y. Okay, so that's like much quicker than we did. We got to that conclusion in the last way we tried this, but we got to it much quicker this way around, right? So kind of working from there, we also can use the second bit here, like use the first one or the YZ one here with the last one, right? So we're going to know that lambda times 2YZ plus XY should equal lambda times 2XZ plus 2YZ, right? The lambdas go away. The 2YZs go away, so I know that XY is equal to 2XZ, which means that Y is equal to 2Z. So now I know that X is equal to Y is equal to 2Z. Okay, so that's a critical notion, right? X is equal to Y is equal to 2Z. Okay, so I have X is equal to Y is equal to 2Z, but I also know from the constraint that 2YZ plus 2YZ let's back that up. 2XZ plus 2YZ plus XY has to equal 12, right? So that's pretty straightforward. So let's see, this is going to be 2 times 2Z times Z plus 2 times 2Z times Z plus 2Z times 2Z is equal to 12. So let's see, 4Z squared plus 4Z squared plus 4Z squared is equal to 12. 12Z squared is equal to 12. Z squared then is equal to 1, which means Z is 1 because it has to be positive. And X is equal to Y is equal to 2 times 1, which is 2. So my maximum has to happen at 2, 2, 1. And lo and behold, the volume at 2, 2, 1 is 2, 2, 1, which is 4, which is the exact same answer that we got using the more algebraic method without using LaGrange multipliers. Now, what's interesting here is that you'll note that we actually didn't find lambda. It's not hard to figure out what lambda is. At the end of the day, if you go from above, clear a little bit of space here, we know that xz is equal to lambda times what is it? Xz, sorry. Xz is equal to lambda times 2z plus x, right? So this is going to be 2, and that's going to be 4. So lambda here is just a half. So lambda does have a fixed value, but we didn't actually need it to be able to solve the problem. All right, so this is like pretty straightforward, but now let's look at how do we use this to solve like some sort of bounded region problem. All right, so let's say that I want to find the max and the min for f of xy is equal to x squared plus 2y squared, subject to a constraint where we're going to let x squared plus y squared be less than or equal to 1. So basically this is the disk contained by the unit circle, and this is the surface that's hanging above that disk. Now, here's what's going on, is that you actually have to use like a two-step method to solve this. You have to deal with one step for where this thing is on the disk, so it's where I'm strictly less than 1, because that's an open region, and that's where we're going to use that D that we did earlier to find the local maximums and minimums. And then I have to deal with where this constraint is on the boundary. So that's where it's equal to 1. And this is where I have a g of x, y equaling to some constant. So this is where we're going to use LaGrange to be able to find the maxes and mins on the boundary. And then we're going to compare all of these things. All right, so let's deal with the interior first. So dealing with the interior, I just want to deal with the f of x, y is equal to x squared plus 2y squared. And I want to figure out where this has local maximums and mins and see if any of those are on the interior. So the first thing I have to do is figure out the gradient. Well, f of x is just going to be 2x. F of y is just going to be 4y. So I need to know when is 2x equal to 0. Well, that's when x is 0. When is 4y equal to 0? Well, that's when y is 0. Okay, so I need to know the second derivatives here. So fxx is going to be 2, fyy is going to be 4, fxy comes out as 0. Okay, so this means d everywhere on this thing is going to be 2 times 4 minus 0 squared, which is 8, which is ultimately always positive. F of xx is 2, which is also positive, which means that at this critical point, 0, 0, I have a local min. All right, so that's the only critical point where I have anything going on here, and it's a local min, and this happens to be inside my domain. So this is an element of x squared plus y squared is less than or equal to 1. It's dead center of that. So it seems like I have a local min there. So now I have to figure out what's happening on the edge of this circle. So this is where I'm solving a reduced problem. I'm going to max or min f of x, y is equal to 2x squared plus 4y squared, right? Or sorry, that's not correct. It's just x squared plus 2y squared subject to g of xy being x squared plus y squared is strictly equal to 1. Okay, so I'm going to maximize that on this boundary. Okay, so I want the situation where del f is equal to lambda del g, right? So del f is equal to lambda del g, and g of xy is equal to 1. Right, so I need the x, y, and lambda that make this true. Right, so we already found the gradient for f, right? So that's just 2x and 4x. The lambdas are there. The x derivative of g is 2x. The x derivative of, or the y derivative of g is just 2y, right? So this helps me out a little bit here, and then I also need x squared plus y squared to equal 1. So I have 3 equations, 3 variables. I should be able to find a solution. So we're going to start by looking at this guy, right? If I look at that guy, I can rewrite that as 2x minus lambda times 2x is equal to 0, which is 2x times 1 minus lambda is equal to 0. So either x is 0 or lambda is 1. All right, so let's do some work here. If x is 0, right, then 0 squared plus y squared should equal to 1. Y should equal to positive or negative 1. So that gives me 2 critical points, 0, 1, and 0, negative 1. And if you put either of these into the objective function, you end up with getting 0 plus 2, so that's going to give me 2. Okay, so these 2 points are either maximums or minimums on the edge, and their values are 2. So the other option is to make lambda equal to 1. So let's see what happens if we do that. Okay, so if we force lambda to equal 1, right, then we know from the second part of the lambda equations that 4y has to equal 1 times 2y, right, which means that 2y has to equal 0, which means y has to equal 0. Using the constraint function, x squared plus 0 squared has to equal 1, which means x squared is 1, which means x is plus or minus 1. So minus 1. Okay, so if x is plus or minus 1, that means I have, let's see, we're going to put in 1 into, so we've got the 2 points. We have 1, 0, and negative 1, 0, and if I put either of these into my objective function, I end up with, let's see, that's going to give me 1 or 1. Okay, so now I end up with a total of 5 critical points, right? I have 0, 1, 0, negative 1, 1, 0, negative 1, 0, and the point 0, 0. This one yielded 2, this one yielded 2, this one yielded 1, this one yielded 1, this one yielded 0. So this is where my maximum occurs, and it's on the boundary. This is where my minimum occurs, which is in the center of the domain, and I have solved the optimization problem both for max and for min over the given domain. So the method for doing this is that you've got 2 parts. You first have to solve using the D discriminant for the region in the center, and then you have to look at the boundary and you have to solve that using LaGrange. Okay, so there we go. Sorry about the long video, but make sure that you trace back through the notes because it's all there, and we'll go forward from there. Thank you.